So I seem to have accidentally gotten everyone's attention. Sorry, I was just putting that up because, of course, we'll be referring to it today. But start, again, by seeing if there's any questions on what we've been doing so far.
Are you going to go over again the algorithm?
Yeah, in fact, well, OK. I mean, drawing it up here was supposed to kind of be going over it. But we're going to go through the details of how to do these parts and what happens if it's not exactly, the period is not exactly a factor of 2 to the n. But yeah, maybe it's worth putting some. So here at this stage, it should be sum over a x to the a. Yeah, OK. So no questions? OK, so yeah, so remember we're talking in the middle of talking about Shor's algorithm, and I gave you an overview of the algorithm and drew it up again here to remind you of the circuit. And so today we're going to talk about how to do these two kind of big boxes and break them up into individual gates. So recall that the basic idea here is that we create this state sum over a x to the a. And when we measure it, we get something that's periodic. The Fourier transform extracts those periods. And the period, of course, is the thing that we're trying to find. So how do we calculate this x to the a mod n? This is basically a classical computation, but of course we're doing it with quantum gates. We need to do it in a reversible way. So let's analyze that. So this is the modular exponentiation step. So actually, before I get into this, there's one somewhat minor point that I forgot to mention yesterday, which is the way I've drawn this, we measure these things, right, and collapse on some particular value y here. So, and then this state will be a sum over what number did I use? J. Of a0 plus jr. But actually, if you'll notice, we don't actually use these measurement results anywhere later on. So it's not actually necessary to measure these things, right? This will work exactly the same if we don't measure at this point. It's just that we'll have kind of an entangled state between this register and things of this form with different values of a0. But eventually the a0, I mean, it's not written up anymore, but eventually the a0 at the end here just becomes a phase, which doesn't really affect the outcome. So that doesn't really matter. It's the r that's important here, which is always there. OK, so modular exponentiation, how do we do that? So I alluded a little bit to this last time when I was talking about RSA, I guess. So the basic observation is that we can, there's two things. So first of all, we can expand A in binary. So it's sum over I, AI 2 to the n minus 1 minus I. I want to write it that way. And so I guess I is here going from 0 to n minus 1. Because this being a computer sciencey sort of thing, we like to start counting at 0. So we count. There's n bits here, n qubits, and so the 2 to the n possible values are 0 to 2 to the n minus 1. So that's why we get that. 2 to the n minus 1, right, which would be all ones in the binary expansion. So what we're going to have to do, so what we're going to do is we're going to break up x to the a into the product of x to these different powers. And we can compute the even powers pretty easily. In fact, we can do that classically. So we compute, well, we already have x. So we compute x squared by multiplying x times x to the 4th by multiplying x squared by x squared, x to the 8th, and so on. Up to x to the 2 to the n minus 1. And this is just, we can just do this classically because these classical numbers will then tell us the quantum part that we have to do there, which is a bunch of controlled additions. So we're going to use some ancillas for this one. So we take A0 to x. So this is the lowest order term. So that's I is equal to n minus 1. So we have, so if a sub n minus 1 is 0, we just don't want to put anything there. If a sub n minus 1 is 1, we want to put x there. So that's x to the a I sub n minus 1. And then here we have x squared to the a n minus 2, and x to the 4th to the a n minus 3, and so on. And here x to the 2 to the n minus 1 to the a0. Okay, so so each one of these is a controlled addition, right? So we're looking at this bit, the n minus first bit, n minus second bit, n minus third bit, et cetera, and we're adding this corresponding value if the control bit is 1, and not adding it if it's 0. Okay, or I guess we're still adding 1 if it's. Sorry, now I'm confused. Oh, right. Sorry, these registers are each log n bits. Right. So either we have 1 or we have some higher number. Okay, and then we have a bunch of these numbers, and of course this isn't quite yet what we want. What we want then is to multiply them together. So now we have a new register, which is going to be the product of these. So that, what is that? That's x to the an minus 1 plus 2 an minus 2 plus 4 an minus 3 plus dot 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 a0 2 to the n minus 1, which of course is just, this thing here is just a. So we have x to the a here. And then we have this other register, which still contains all of these things. Okay? And so then the last step is that we uncompute the controlled additions. To get just a, x to the a. And then these other registers are all 0. Okay? Does that make sense? And this is another example of a case where it's really important to do this uncomputation, where we have to get rid of these intermediate scratch bits. Because if we had them, we could tell exactly what A is. But we don't, from this register. Right, but we don't want to do that. I mean, A is held here, but we want a superposition over different values of A once we get rid of these ancilla registers. Okay, just the values of A that have a particular value of x to the A. Okay. Yeah. Yeah, it's not so bad, right? Because how many of these things are there? There's little n of them. And each one is log n bits, so which is kind of comparable. So it's grown. But actually, this is kind of the clumsy way to do it. You don't really need to do it this way. What you could do is you can add one here, and then, well, this is something that we can kind of compute as one gate. And instead of adding this to this gate, to this register, we just multiply this one by this new amount, right? And that's a perfectly valid gate as well. It's reversible, right? Because we're doing something that just depends on this, so we could easily undo it. And then you can keep on doing that. So actually, you only really need the one register if you want to save the space. But for simplicity, let's just do it this way. Other questions?
At what step are we taking mod n? I mean,
We're doing it all the time. All of these things are mod n. There's no point in ever kind of going bigger than that, right? Because the mod n is a closed ring, so you can do all the arithmetic there. And
that sort of happens kind of automatically.
Yeah, well, I mean, okay. So actually, so actually, it's already happening up here, right? In that, okay, so I'm going to square x. So if x squared is greater than n, I'll just take it mod n, right? And x to the fourth. So look, so x to the fourth mod n is going to be equal to x squared mod n squared mod n. Right, so then this is the kind of the consistency that we need. That it doesn't matter, if we take it at every step or just take it at the end, we'll still get the same answer. Okay, because when you square the multiples of n, will still be multiples of n.
In terms of actual data storage, I think this is right, but if
right.
if n is is a power of 2, then taking a mod of something is just truncating it.
That's right. N is not a power of 2, obviously, because if it were, we wouldn't need all this effort to factor it. But nevertheless, it's kind of so then it's an actual computation if you have to subtract off some multiple of n until you get something that's less than n.
How do we do that if we're only storing log n bits? Like, at what point do we store something?
Well, no. So the point is, So the point is that when we calculate x squared mod n, so we multiply x by x, we might get something that's bigger than n. If so, we'll subtract off n, or we'll take it mod n, which means subtract off enough multiples of n to get something that's less than n. So in the intermediate there, you may end up using one extra bit or something, but that's not a big deal.
When we write these qubits of like x to the a n minus 1 and stuff, sorry, are they is that still a qubit, or is this like a?
No. So each of these registers should be log n bits, because they're numbers that are mod n, so they could be quite large. Yeah.
So would we ever have problem factoring with even numbers because of like the internal kind of there's no 2 inverse there?
Yeah. So actually, that's correct that Shor's algorithm doesn't work for even numbers, but there are other methods for factoring even numbers. So that's something you should check, right, before running Shor's algorithm. But this is obviously not a big deal for the algorithm as well. Okay, so maybe the next thing to do is to count the number of gates that we actually used here, because we should check that that's not too many. Okay, so we have various steps. So what's the gate complexity? Okay, so the classical pre-computation. So each time we're getting a new one of these by multiplying 2 of the old ones together, right? So there's a total of n minus 1 things that we're calculating here, or yes, n minus 1. So we need n minus 1 multiplications. So these controlled addition steps, there's also n, is it n minus 1? No, there's n of those, because we have powers 2 to the 0 up to 2 to the n minus 1. So the controlled additions there's n minus 1, sorry, n of those. N of them. And the multiplication, well, again, we have multiplications. We have to multiply together these n numbers. So there's n minus 1 multiplications. And again, at every step, along the way here, we can reduce mod n, big N. And then the uncomputing is, again, n controlled additions. OK, but each of these steps can take some extra time. So the controlled additions are not so bad, right? That's we have some fixed number, basically, that we're adding, or one of two numbers, depending if the bit is 0 or 1. And we're so that's something that you can do basically in linear time, in the number of bits, in the log n bits, right? You just have to add and keep track of the carry bit. So that's kind of order n. Order n squared effort altogether. But the multiplications take a bit longer. So if you use kind of standard long multiplication, well, we're multiplying together numbers that have log n bits, right? And so we have to take basically all pairs of bits and then add all of that up. So that takes a time that's log n squared. Now, there are faster ways of doing that. There's these fast multiplication algorithms that people have come up with. So that will reduce the time. But if we just use this method, then the total is, well, we have about 2n multiplications. So again, ignoring constants, we get O of n log n squared. OK. And in fact, we're going to pick n to be O of log n. So then this is O of n cubed. But with fast multiplication, you can get that down to O of n squared log n log n. So this is log little n. OK. So yeah.
Is that fast multiplication classical?
Yeah, this is just a classical thing. People have not come up with a way to speed up multiplication using quantum computers. I think there's some ideas for kind of reducing the amount of scratch bits that you need. But it doesn't mean that there isn't a way to do it. It's just no one's come up with something. OK? Everyone OK with the modular exponentiation? OK. So this is all basically really just a classical algorithm. I mean, I put kets around these because we need to do it in superposition. But it's all the gates that are involved here are classical gates. I mean, it's just, you know, they're CNOT gates and Toffoli gates, but we're implementing them in qubits. But now the Fourier transform, of course, we're going to have to do something that's really quantum, because we're changing the basis. So that's another page. So remember what we're trying to do with the Fourier transform is this operation. With omega is e to the 2 pi I over 2 to the n. Okay, so how do we do this? Again, we're going to expand A and B in their binary notation. So you have A is equal to A0, 2 to the n minus 1, plus A1, 2 to the n minus 2, plus A2, 2 to the n minus 3, plus dot, 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 plus an minus 1. And B is equal to, similarly, B0, 2 to the n minus 1, plus B1, 2 to the n minus 2, plus B2, 2 to the n minus 3, plus dot, 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 plus Bn minus 1. And then when we multiply them together for this power of omega, what do we get? Well, we're going to get, you know, A0, B0, 2 to the 2n minus 2, and lots of other stuff with high powers of 2 to the n. But anything that's bigger than 2 to the n, or any multiple, any power of 2 that's bigger than the nth power of 2, is just going to cause, is just going to be an integer, 2 pi I times some integer, right? And so that will be 1 in the exponent. And I mean, sorry, it'll be omega to that will just be 1. So we can take it out of the exponent. So it'll be something here times 2 to the n, and we don't really care what's there. We can kind of ignore that. So let's start counting when we do this multiplication, things that have powers of 2 to the n minus 1 or less. So, so what's the coefficient of 2 to the n minus 1? Well, we get A0 Bn minus 1. And A1 Bn minus 2, and so on, down to A n minus 1 B0. And then we have the power of 2 to the n minus 2, which is going to be, well, there's no A0 term, because that's already higher. So we have A1 Bn minus 1 plus A2 Bn minus 2 plus dot, 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 plus A n minus 1 B1. And then, of course, we keep doing this. And then finally, we have the last term is going to be 2 to the 0, A n minus 1, B n minus 1. OK? This should be clear, I hope. OK, so let's expand that out up there and try to figure out how to actually get that to happen. So it turns out that it's convenient to write B in sort of the reverse order from A. So if we're writing A0, A1, A2, et cetera, we're going to write B as B n minus 1, B n minus 2 down to B0. So we have the thing that we're trying to get is this, which looks like this. And then by plugging in this expression for AB, I want to take out the terms here that depend on Bn minus 1. And so what do I get? Well, so let me sum over bn minus 1. So I can separate that out and sum. And I have omega. So what are the bn minus 1 terms? Well, here we have a0, 2 to the n minus 1. And bn minus 1, so we have a1, 2 to the n minus 2. And so on. We have a2, 2 to the n minus 3, all the way down to this last one, which is an minus 1. All of that times bn minus 1. And then we have the ket here, bn minus 1. Okay, and then let's do the same thing for bn minus 2. We'll take out the sum over bn minus 2. And so we have omega to what power? Well, we have, so bn minus 2 first appears here with a1 and 2 to the n minus 1. And then we have a2, 2 to the n minus 2, and so on down to a n minus 1, 2 to the power 1. Because we're bn minus 2 here. Okay? Okay, and similarly, we keep on going like this. And then we have, at the end, we have sum over b0, omega to the a n minus 1, 2 to the n minus 1, b0. Okay, b0. Okay, so let's look at this more closely. So what you see here is that we've factored this expression into a tensor product of terms. This is the image of a basis state, of course. In general, it doesn't have to be a basis state that's input. But if we have a basis state, then we factored the output into a tensor product of single qubit terms that have some phase. And so what we want to do is we want to figure out what that phase is. And obviously, the phase depends on all the input bits, potentially, or certainly many of them. So what in general is the power of omega? So we have kind of what's the intermediate term here. So what it is a sum over bn minus I. And so there's going to be a ket bn minus I here. And then we have the power of omega to the, well, it starts, what does it start with? Well, the bn minus 1 starts with a0, bn minus 2 starts with a1. And so in general, the bn minus I will start with I minus 1. And that's always next to 2 to the n minus 1. Okay? And then we have some sum of the smaller ones, which are sum over j greater than or equal to I, aj 2 to the n minus 2 minus j minus I. And then this thing, sorry, I didn't leave enough space. This thing times bn minus I, and we have the ket bn minus I. Okay? So this is just kind of putting this in a slightly more closed form. And the whole thing, of course, is a tensor product over I of these. Okay, everyone still with me? Okay, so sorry, maybe that's too high. So what I want to point out, so this thing, of course, is a product of this thing here is a product over of various powers of omega. So we have omega to the to the first one, to the ai minus 1. Here, let me rearrange slightly. So it's omega to the 2 to the n minus 1 to the ai minus 1. And then the product of omega to the 2 to the n minus 2 minus j minus I to the aj. And bn minus I in here, bn minus I. Right? And so this thing, of course, omega to the 2 to the n is 1, but omega to the 2 to the n minus 1 is minus 1. So this is, yeah. So, so this is minus 1 to the ai minus 1 bn minus I times the product of e to the 2 pi I over this over 2 to the n. So it's 2 to the 2 plus j minus I. And then this to the power aj bn minus I. Okay, so so this you see. Okay, so so now the next important thing is to observe that because we've reversed the order, the a sub I minus 1 is held. So a sub I minus 1 is the ith qubit of the input. And b sub n minus I is the ith qubit of the output. Right? So this thing is giving us a phase of minus 1 if the ith qubit of the input was 1 and the ith qubit of the output is also 1. So we could achieve this phase just in isolation by doing the Hadamard on the ith qubit. Right? And then we get exactly what we want, in fact. Again, ignoring all of this stuff. Because we then have this, actually the sum over bn minus I minus 1 to the ai minus 1 bn minus I ket bn minus I. Okay? So, and then all of these other phases are basically controlled gates between the larger numbered qubits of the input. So j plus 1. Remember, j is starting at I and going higher. So j plus 1th qubit of the input with the ith qubit of the output. So if we first do the Hadamard on the ith qubit, then we get this phase right. And then, before we've done stuff to the later qubits, we do controlled phase gates by this appropriate phase. Okay, so let me write that out. So we're going to start out. With the input here, A1, A2, down through an minus 1. And we start out with a Hadamard on this first qubit. Okay, but then we want to do controlled phase gates. So, so this is controlled R pi over 2, using the notation we had before. And this one here is controlled R pi over 4. See, because the phase here depends on the difference between these two. So the first one here is always going to be a pi over 2, and the second one, it's a pi over 4. And then we keep on doing these until we have a controlled R pi over 2 to the n minus 1 down here. Okay? And once we finish that, the first qubit is done. We've gotten exactly what we want for it up there. Okay? But now we have to start on second qubit, right? So we do the Hadamard here, and then we do another controlled r pi over 2, and then controlled r pi over 4, controlled, etc., all the way down until we have a controlled r pi over 2 to the n minus 2, right? Because it's not as far away from the second qubit as from the first qubit. Okay, and so then once we've done all of that, we're done with the second qubit. So we start on the third qubit. We do a Hadamard. We do a bunch of controlled things, and eventually we get r pi over 2 to the n minus 3 down here. I know you can't see those, but hopefully you hear. And so then we're done with the third qubit, and of course we do the fourth qubit, fifth qubit, etc. And then finally we end the whole thing with a Hadamard down here. And the output we get is Bn minus 1, Bn minus 2, Bn minus 3, down to B0. Okay? So does that make sense? So the last thing that we want to do then is count the complexity. Of this Fourier transform step. And that's easy to do. I mean, so we have a bunch of, so for each qubit, we have a Hadamard, and then we have 2 qubit gates between that one and all the later ones. So basically, we have 2 qubit gates between all pairs of qubits and Hadamards for each one. So that's order n squared gates. Okay. So what we find is that the complexity of Shor's algorithm actually dominated not by the Fourier transform, which is the more quantum part, but by the modular exponentiation. So so it's order n cubed if we use kind of simple multiplication, or that n squared log n log log n if you use faster, or somewhere in between if it's an intermediate. Okay. So is everyone with me so far? Okay, so are there any questions on the Fourier transform? Okay, so then the last thing I want to do is discuss what happens when r is not a factor of 2 to the n, which of course will be the typical case. So recall that yeah. So the Fourier transform doesn't, right? So the Fourier transform is the Fourier transform over 2 to the n minus, well, 2 to the n, z mod 2 to the n. But of course, little n depends on how big the number you're trying to factor is. The place where where big N really comes into it is in the modular exponentiation, because all of that is done mod big N. Okay? And so that's what generates the periodicity in the first place. The Fourier transform, you can give it anything, and it'll extract the periodicity of that. Right? And so it's big N is only coming in to the first part where it determines the periodicity in the first place, in the initial state. Yeah, so that's the normal way people talk about it. I mean, it doesn't, you can have a kind of more complicated sort of semi-programmable circuit where you have, I mean, where you have some input register. I mean, this is kind of how a regular computer works. We have some input registers, and you do additional controls that, you know, tell you what these x squared, x fourth, et cetera are. I mean, usually in the case of a quantum computer, we're imagining that there's going to be some classical computer that's controlling the quantum computer. So we don't bother with all of that stuff. But in principle, you can do that.
Would it affect the complexity a lot?
No, not really. Not really. I mean, it's constant factors, I think. Yeah?
You know, the classical complexity of the Fourier transform?
Well, OK, so this is the quantum Fourier transform. So it's not something you can do classically. Right? It's changing the basis. Classical, the fast Fourier transform classically, I mean, is I think it's also, yeah, I don't remember. But it's a function now of the range, right? So it would be like big N squared or something like that, or I mean, this is kind of very closely related to the fast Fourier transform in terms of its structure. But basically implementing this Hadamard, instead of being a 1-qubit gate, well, you're kind of doing, I mean, you have this whole function on n values, and you're kind of changing half of them or something, or even all of them. So that's kind of where that comes from. Yeah.
I think I'm missing something conceptually.
Mm-hmm.
It's, like you just said, the quantum Fourier transform isn't something we can do classically, and you know, I can see that if I put in a computational basis state, you know, classically that has some Fourier transform and I can compute it. But here I end up in a superposition of all.
Yeah, that's right. So there is no Fourier transform of a classical. Classically, there's no Fourier transform of a single number, right? You Fourier transform functions.
Right.
Okay. And in this case, the function is stored in the amplitude of the quantum state. So the actual function is, well, the input state is some alpha n, or alpha, what did I call it? Alpha A.
Mm-hmm.
Okay? And alpha A is the function that we're Fourier transforming it. And we're Fourier transforming it not into some output description of the function, but into the amplitude of the output state.
Mm-hmm.
Okay? So it's a function, Fourier transform takes functions to functions. So classically, you'd kind of have to list all of that out and then do the Fourier transform on that whole function. Here, we're just doing it in the amplitude, so that's why it's much faster.
So when you've written this up here, like f of a is sum of omega a b b.
Right.
We wouldn't really actually do that on a basis state a. We would do it on
No, that's right. And in fact, if you look at that algorithm, we're definitely not putting in basis states.
Mm-hmm.
Right. But it's just convenient. I mean, describing it what happens on the basis is sufficient to describe it everywhere by linearity. And it's easier to think about how to do it by. Now, I mean, there is some kind of maybe minor subtlety that one might have to worry about when you're thinking of well, OK, I'm doing this on a basis state. How do I make the basis state work right? Which is, if there were kind of global phases that appeared somewhere along the way, I have to be careful of those because if they're different for the different values of A, then that's not a global phase anymore, it's a relative phase, and it has real meaning. If it's always the same phase that appears for any value of A, then it doesn't matter. But like, I can't just say, oh, this thing, you know, it depends on the ith bit of A, but let's ignore that. And then obviously nothing would happen, right? Then you'd be doing something that doesn't work. So, but basically working on the basis states is frequently a good idea just as a simplification. Yeah?
What about the classical processing stack?
Yeah, so I haven't gotten to that yet. So I mean, I told you yesterday what happened in the special case where R divides 2 to the n.
You still have to repeat it many times.
Yeah, you have to repeat it a few times. Yeah, not actually many times, but that's correct. But yeah, so in fact, the complexity will be slightly higher because you're repeating it. But it turns out that that's kind of, again, a constant.
So it doesn't depend on the size of the input, the number of times you have to repeat.
No, not really. I don't think so. But exactly what the post-processing is a little more involved in the real case than in that special case. So I'll get to that in a minute. Other questions? OK, so then let's talk about what happens when R does not divide 2 to the n. So when R does divide 2 to the n, we had something that looks like this as the input to the Fourier transform, right? With exactly very sharp spikes and exactly distance R between the spikes. And then the Fourier transform took that to something that had some phase, but basically had distance 2 to the n over R between the spikes. But when R does not divide 2 to the n exactly, well, we still have something that's kind of almost periodic. We have we still have this state, right? This part didn't depend on R dividing 2 to the n. But the problem is that when we wrap around, when we go from 2 to the n minus 1 all the way back to 0, then there's kind of a glitch in the periodicity. So the input here still looks like this. So this is when R divides 2 to the n. The input here still looks like this, but because this thing here is a little bit different, we have some extra frequencies that are appearing. And so what we get under the Fourier transform is not this, but something that looks more like this. We get things, they're still peaked around spikes, but they're not infinitely narrow spikes. They're spikes with some finite width. And the distance between these things is still 2 to the n over R. And actually, I should. So this is 0 here, in fact. I mean, because the overall shift is disappearing. That's kind of the important thing. Otherwise, it wouldn't turning into the phase. Otherwise, just measuring wouldn't give you the right answer. So the highest values here are going to be about 2 to the n over R. But of course, 2 to the n over R is not an integer. So we're going to get something that's close to 2 to the n over R. And because this spike has a finite width, we might not even get the closest integer to 2 to the n over R. We might get something that's a couple off. So how are we going to deal with that? So as we make little n bigger and bigger, these spikes are going to get narrower and narrower, right? Because the non-periodicity only happens at the very end. So it becomes a smaller and smaller perturbation of the periodic structure. So it turns out that if we choose little n to be so that 2 to the n is kind of roughly big N squared. So little n is then going to be about 2 log big N. Then we're going to get peaks that are narrow enough for this whole thing to work. And I'm not going to go through kind of the details of this, but what we have to do with the post-processing is we have to take, again, we repeat this a few times. We get a couple of examples of numbers that are close to multiples of 2 to the n over R. So we get outcomes that are close to C 2 to the n over r. And the actual thing we get, I'm going to call it B, because that's what we were using before. And the point is that we want to compare B over 2 to the n to C over r. And our real goal is to find C over r. Or really, we want to find r, of course, but we're going to do this a couple times and have some different values of C here. So it turns out that the way that seems like the best way to analyze this is using something called continued fractions. I don't know if people have heard of continued fractions before. But the basic idea is continued fraction is going to be something that looks like this. So you write it, say, as an integer plus 1 over, doesn't really have to be 1, but in this case it is, something that's of the same form. C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. And in principle, this can keep going infinitely. But for rational numbers, this terminates. And this is a rational number. And there's a nice efficient algorithm to calculate this. In fact, it's pretty obvious, which is you look at this, you subtract off, the integer part of it. You're left with 1 over something. So you take 1 over that, and then, well, you subtract off the integer part of that, and then invert and subtract off the integer part of that. And at each point, you record what you get, C0, C1, C2, C3, et cetera. Okay? And so it'll terminate, and not that long. I mean, it's something that depends on n, little n. It turns out that when these two things are sufficiently close, which is what happens when little n is big enough with high probability, then these two things have basically the same continued fraction expansion. But this one terminates sooner. Okay? So what's the post-processing procedure then? Well, you take a couple of these b's, you calculate these continued fraction expansions for them, and then you imagine truncating them at various points to get candidates C over R. And then you compare these different values of C over R that you get to try to find the common denominator R. Okay? And then once you do that, that's your candidate for the period. Assuming you find, I mean, it could have been that you just got some weird bad luck and that they were all far off from the peaks, and so it's wrong thing. It could be that you got C's that are all have common factors with R, and so you're actually getting only a factor of R. But whatever, the odds of getting the actual R are pretty good. And so after comparing a few of these, you should be able to get the actual R out. And just to be sure, you can try it out or go ahead and figure out factors based on it and try those out. Okay? Yeah. I'm sure there's some number theoretic reason. Yeah, sorry, I don't know enough about continued fractions to really answer that. I mean, maybe the relevant, possibly the relevant thing is that R is just smaller than 2 to the n. So the denominator is smaller. But yeah, I'm not sure exactly. Okay.
Is that
Sorry, what does it mean? You mean you get one of the factors, but not the actual factor, but the factor minus 1? Okay, so that's not going to happen. If you come up with an R that's off by 1 from the true R, it just won't work. You won't get a factor at all. You'll get something totally different, right? Because you're taking the GCD of these things. And if somehow you did get the wrong factor, I mean, you should test your factors to make sure that they work. But if you get the wrong thing, even if it's close to the right one, when you exponentiate, so in RSA, how do you decode? Well, you have to figure out what this D is, right? And if it's the wrong D, even if it's just 1 off, you decode by taking y to the power d, but you'll get something totally different, right? So if it's 1 too high, you'll get I guess you'll get x to the whatever. You'll get something that's just wrong. Okay, which usually is pretty obvious because then you plug it in, you try to decode the message, and you get gibberish. It's conceivable, but unlikely that it will be a sensible message that says something else altogether. But that's really unlikely. Most messages are going to be gibberish. But the easiest thing to do is just test the factor, because that you can always tell. Other questions? Okay. So at this point, I don't think it makes sense to start Grover's algorithm. So we'll do Grover's algorithm tomorrow. So Grover's algorithm is a search algorithm. So it's good if you have a kind of a long list of things you want to try. And what it does is it speeds up that search from trying all n things, or order n things, to order square root of n things. So it's not an exponential speed up like Shor's algorithm. Shor's algorithm is taking exponential time in log n down to polynomial time, or at least sub-exponential time in log n. So it's a huge speed up. It's something that you couldn't really imagine doing on a classical computer. Whereas Grover's algorithm is only a polynomial speed up. So if you had a big enough classical computer, then it would help. But nevertheless, it's still a big improvement if you're imagining some very large classical algorithm that you're speeding up to the square root of its time, right? Going down from n squared time to n time is already a big improvement. Going from 2 to the n time to 2 to the n over 2 time is a big improvement, right? If 2 to the n is 10 to the, 10th, then the square root of that is 10 to the 5th, which is much more reasonable. And there's a tutorial today, and you're going to do another algorithm altogether, which is the Hamiltonian simulation algorithm. So so factoring, if you're the NSA or CSEC, maybe yes, you're really interested in breaking RSA. Most people probably not going to want to do that themselves. So one of, I think, the most practical algorithms is this quantum algorithm for simulating other quantum systems, which, again, most people are not going to want to do that themselves. But here at PI, a lot of physicists probably would be interested in doing that. And it's also something that's kind of interesting to chemists and other people who deal with quantum systems. And it uses some of the same ideas that we've seen here. So that'll give you more practice with quantum algorithms. Okay.